All right. All right, so we're going to talk about, today we're going to talk about vector fields and the curl. And tomorrow, let's get started, guys. Let's get started. Tomorrow we'll talk about, let's focus. Tomorrow, so today vector fields and the curl. Tomorrow we'll talk about divergence. So we'll learn some new terms. We'll get to learn some new symbols in this chapter, some new math symbols, which is always nice. All right. So we want to introduce the idea of a vector field. So we'll go back to just a normal function. A normal single variable function assigns a scalar to a scalar. So we plug in x and we get y. X is a scalar, we get another scalar. Then we talked about a multivariable function assigns a scalar to a point in the plane or a point in space. So we plug in x and y and we get a scalar out. We plug in x, y, and z, we get a scalar out. We just get a number. So those are multivariable functions, just give us a scalar. Assign a scalar to a point in space. We also study parametric equations or vector valued functions. They're kind of related. And vector valued functions assign a vector to a scalar. So our parameter is a scalar. Often we use time. And a vector valued function assigns a vector to that scalar. So at a particular time, our velocity vector is this. So that's a vector valued function. What we're going to talk about in this chapter is a vector field. What happens with a vector field is we are assigning a vector to every point in space. And if we're in the plane, it assigns a vector to a point in the plane. And where vector fields come up often are velocity fields. So if you have, for example, a liquid that's moving around, you can assign a velocity vector to every point in that liquid. So every point in that liquid is going to have a velocity vector. A magnetic field, you have a magnetic field, you have a field vector assigned to every point in space. Same with a gravitational field. You have a vector assigned to every point in space that has to do with the gravitational field. So those are some examples of vector fields. What is a quantity that we've worked with quite a bit that is also a vector field? What thing do we know about that assigns a vector to every point in space? What's that? A slope field, yeah, so a slope field would assign a slope so you'd have a direction. So that would be a slope field. I'm thinking something more recent that we worked with. The gradient. The gradient is a vector field. We will use a gradient a lot in chapter 15. So we have a del of f of x, y, z. F of x, y, z is just is a scalar. But this is a scalar assigned to a point in space, and we set our gradient just as a reminder. Partial derivative with respect to x, I hat, plus partial y, j hat, plus partial z, k hat. So that assigns to the point x, y, z, it assigns this vector, the gradient vector. And we remember that our gradient is normal to level surfaces and normal to level curves in the plane. And that, yes.
You wrote X, Y, Y.
Oh, X, Y, Y. Z, thank you. I was just excited to be talking about the gradient again. So our gradient is a vector field. That's a vector field that we'll use quite a bit. Now the terminology, the way that the notation that we're going to use is we will say our notation f of x, y in the plane is we're going to usually say m I hat plus n j hat, or if we're in space, we have our vector field x, y, z. And we say m I hat plus n j hat plus p z hat. And m, n, and p are functions of x, y, or x, y, and z. So we plug in a point and we get out a vector. Now the first thing we want to do is talk about how we visualize. Yes. Oh, k hat, z hat, k hat. There we go. The first thing we want to do is given a vector field, some description of a vector field, to be able to visualize it a little bit. So one way that we can visualize a vector field, or help a tool that will help us visualize a vector field. So I'm going to say it's not always necessary to visualize a vector field, but sometimes it's nice to be able to have an idea of how these vectors are behaving. So we can always just plug in numbers into our function for our vector field and plot those vectors. But we want to have some tools to be able to do it in a little more systematic way. One tool that we can use, so we can plug in numbers. And just plot vectors, sketch little vectors. It is also helpful to look at where the magnitude is constant. So we look for a constant magnitude, and sometimes that will give us an idea of how this vector field is behaving. Looking at where the magnitude is constant is very similar to finding level curves. We're finding where the magnitude of the vector is constant. So kind of like what we did with level curves. So what I want to do is take a look at some graphs or some equations, and we want to match them to graphs of the vector fields. So let me grab this. Where did I put it? Go. And let me grab a picture of that. Go on the page. All right, got a little bigger. All right, so there are we want to match these vector fields to their graphs. So number one says f of xy, this vector f of xy is y equals y, these are equal signs, equals y I hat. So the way I look at this one, first thing we see about this is it only has an I component. And the vectors are going to have the same magnitude at a particular y value, so along a horizontal line. So which vector field only has a y component and the magnitudes are constant for any particular or only have an x component, yi, only have an x component, and their magnitudes are constant for any particular y value? D. Well, this is the one that has, so we only have an x component, and for any y value along the horizontal line, our magnitudes are constant, and the magnitudes are increasing as we go, as y gets larger, positive or negative. So this would match with, number 1 would match with D. All right, number 2, f of xy equals x j hat. So kind of almost the opposite thing. That would be C. We only have a y component, and the magnitude is constant for any particular x value. So along a vertical line. So that would be, match that vector field. So that would be C. All right. yi minus xj. Seth says A. What makes you say A? They're subtracting from each other. So this is one. Number 3, this is one where we could think of, look at the constant magnitude. So for number 3, what I look at is the magnitude of f equals the square root of x squared plus y squared, and that equals a constant. So we're looking for where the magnitude is constant. I'm going to square both sides. X squared plus y squared, c squared is some other constant, so some other constant k. So x squared plus y squared equals k. So the magnitude is constant on a, what kind of shape? A circle. Magnitude is constant on the circle. Here we have constant magnitude around a circle. And then we can look at the, if we still weren't sure, we could look at how the direction the vectors are pointing. So this is, we're getting a yi minus xj, and we would see that the direction that these vectors are taking around that circle match with this description. So this is an example of where we could use that idea of the constant magnitude to help us visualize that field. So this would be, number 3 would be A. And of course that leaves B for 4. But if we just had this equation and we needed to figure out what it looked like, we could apply the same thing. So just to go through the process there, for number 4, and this should be a magnitude of f, magnitude of our, we want those constant. So that's going to be the square root of x squared plus 9y squared, and that is, we want where that's a constant. So x squared plus 9y squared is some other constant. Divide everything by 9, and I get x squared over 9 plus y squared equals some other constant. And we get a constant magnitude on an ellipse with a horizontal major axis. And that matches with the way B is drawn. So just a little bit on how we might visualize a vector field to sketch a graph. All right, questions there? I love vector fields. All right, next important idea, and this will be something that we use throughout the chapter. The idea of a conservative vector field. Conservative vector field doesn't have to do with their voting behavior. We're going to define a conservative vector field if our vector field, if f equals the gradient of some scalar function. and f is differentiable. We call f, our vector field, capital F, is conservative. So if our vector field is the gradient of some scalar function, we call our vector field conservative. And f, small f, is called the potential function. And we're going to do this several times in this chapter, where we come up with a term, we come up with a description. We're going to have to defer a little bit, talking about what this means, until we have a little more background. So we'll talk about what a conservative field conserves a little later, and we'll talk about what a potential function means a little later. Now, a lot of the terminology comes from physics, because this vector analysis, vector calculus, was developed right around the time that electromagnetism, the electromagnetic theory, was being developed. So they kind of developed concurrently, and a lot of this was developed to describe electromagnetism. So the terminology that we use comes from physics. So the terminology is going to be familiar from physics, and our descriptions are going to be familiar from physics, because they develop kind of in tandem. All right. So we have a potential function. This gives us, we've decided the gradient is a vector field. If our vector field is the gradient of some function, then our vector field is conservative, and we call the scalar function the potential function. All right. So a quick, easy example. If the question asks you, we have f of xy, and we have 3 cosine 3x cosine 4y. And the question asks us, find the conservative vector field for this potential function. So they're giving us a potential function. So this is just a fancy way of saying find the gradient of f. To find our conservative vector field, we're finding the gradient of f. So what it's asking us to do is find del f. So we find our gradient, we take our partial derivatives, del f, take our partial with respect to x, and we get and actually let me switch this. I want this to be sine of 3x. Sorry. Sine 3x. So del f is 3 cosine 3x cosine 4y I hat, and we take the partial with respect to y, minus 4. And this should be that should be a 9. 3 times 3 is 9. Minus 3 times 4 is 12. Minus 12 sine 3x sine 4y. J hat. So that would be this would be a conservative vector field. So a question like this is asking us to find the gradient. Well, so if we're given a vector field, we want a way to tell. How do we tell, is this vector field conservative? We have a nice test for conservative vector fields. So if we're given some vector field, we want to be able to tell, is it conservative? Because if it's conservative, there are problems that we're going to solve later that the fact that the vector field is conservative simplifies our problem significantly. All right, so in the plane, so we're talking about a vector field in the plane right now. So f of x, y, our vector field is mi plus nj. This vector field, f of x, y, is conservative if and only if dm dy, the partial of m with respect to y, equals the partial of n with respect to x. And we're saying m and n are nice functions. They have continuous partials. So this is our test for conservative vector fields. Take the partial of this function with respect to y, partial of this function with respect to x. Now thinking about what we just talked about, does anyone have an idea of why this might tell us, why this might be the test for a conservative vector field? So if it's a conservative vector field, m is the partial derivative of our potential function with respect to x, and n is the partial derivative of our potential function with respect to y. These two represent the mixed partials of our potential function. So if this comes from a potential function, these are our mixed partials, and the mixed partials should be equal. So what we're saying is, if f is the gradient of some potential function, f sub x equals m, and f sub y equals n, and f sub x y is the partial of m with respect to y, and f sub y x is the partial of n with respect to x. And our mixed partials are equal. So if this comes from a potential function, these are our mixed partials, and they would be equal. So already just in the very first section of chapter 15, we've talked about vector fields, we talked about the gradient, and now we're talking about partial derivatives and mixed partials. So we've got chapter 12, chapter 13 already mixed together here in the first part of chapter 15. All right, so what we want to do, I want to do an example with a potential function in the plane, and then we'll talk about our test for conservative vector field in space, and we'll get to this idea of the curl. And we also, when we'll do this example, we'll come up with if our vector field is conservative, how do we find the potential function? We can find our potential function, and this relates to a bonus question I put on the chapter 13 test. Let me see, is this the example? Yes. So we want to see, is the vector field conservative? That's our first question, and if so, find a potential function. So here's our vector field in the plane. F of xy is 3x squared y I hat y squared I hat plus 2x to the third y j hat. So for this vector field, we're saying that m is 3x squared y squared, and n is 2x to the third y. And we're going to test our partial derivatives. So the partial of m with respect to y, take that partial derivative, and I get 6x squared y. Partial of n with respect to x, and I get 6x squared y. So that says it is conservative. So now we need to find our potential function. So for our potential function, if this is the gradient of some scalar function, we need we know that f is the gradient of some potential function. So we need the partial of f df dx has to equal 3x squared y squared. And we have the partial of f with respect to y has to equal 2x to the third y. So what we're going to do is integrate each of these separately to come up with our potential function. So f has to equal the integral of df dx, this partial, with respect to x. So I'm going to integrate this with respect to x. And when I integrate this with respect to x, I get x to the third y squared. And here's where I have to be careful. My constant of integration could be a function of y. Because when I differentiate with respect to x, a function of y is going to be constant. And that function of y could go away when I take my partial derivative with respect to x. So this is my constant of integration. So I'm going to put that in. So that's my constant of integration with respect to x. And then I'm going to do the same thing for the second partial derivative. I'm going to take the integral of df, the partial with respect to y, integrate that with respect to y. And I get 3 partial df dx, 2x to the third y dy. And when I integrate that, I get, did I do this one right? Yes, 2x to the third y. Yeah. So when I integrate that with respect to y, I get x to the third y squared plus some constant of integration with respect to x. And now what I do is I look back at, because there aren't any stray x or y terms here, I don't have a function of y here I don't have a function of x here. So my constants of integration, these turn out not to be functions of x and y, but they're just constants. So I don't have any extra terms that I have to take into account here. When I take, so my constants of integration are not functions of x and y, they're just some constant. So f equals x to the third y squared plus some scalar constant. What's that? K is just some, you could say C. I just called it K. And this is a scalar constant. So we don't have the way, and the way I figured out that this was just a scalar constant is because we don't have any extra y terms or any extra terms here that we have to take into account with my scalar function. All right, so there's our potential function. Questions on how we came up with our potential function? And occasionally we'll come up with a potential function where this could be where you could end up with some extra term that's some function of y, or an extra term with some function of x, that when you take your partial derivative with respect to y or with respect to x, they would go away. Most of the ones we work with, I think there might be one in your homework where you end up with a function of x or y when you do your integration, but most of them turn out pretty nice. All right, so let's talk about the curl of a vector field, and then we'll talk about our test for conservative vector fields in space. So the curl of a vector field. Curl is another one of those terms where we will talk about what it is, we'll calculate it, but to give it an interpretation, we really need to wait almost until the end of the chapter, and we'll have an interpretation of the vector of the curl. All right, so curl of a vector field, we need a vector field in space. So here's our vector field. The curl of f and we'll write, you'll see it written a couple of ways. We can just say the curl. Just use the word curl. Equals del cross f. And del cross f, we'll write it out, and then we'll talk about how we calculate it. And that's going to be the partial of p. And we're not going to memorize this because we'll have an easy way to do this. Dy minus the partial of n dz I hat minus the partial of p with respect to x minus the partial of m with respect to z j hat plus the partial of n with respect to x minus the partial of m with respect to y k hat. Now here, this is another example of where we're using del as a vector operator. It's operating on another vector. When we did the gradient, del operated directly on a scalar to give us a vector. Here we're taking the cross product of this vector operator with another vector. So del, remember we defined del, 3 equal signs means defined, d dx I hat plus d dy j hat plus d dz k hat. So we can simplify this notation for del cross f for the curl as this determinant. So this is how we're going to calculate the curl. We put our components of our vector field here, and we form this determinant. So this is our curl. The curl in general, we'll say that the curl tells about the tendency of a vector field to cause a rotation. And it's a little more complicated than that. But that's the curl gives us that an idea of that. If our curl is 0, we call the vector field irrotation. So if our curl is 0, that vector field doesn't tend to cause rotation. We call it irrotation. All right, so what I want to do is do an example of do a curl calculation, and then we'll talk about our test for conservative vector fields. Our test for conservative vector fields in space has to do with the curl. So let's find the curl of this interesting vector field. Find the curl of here's our vector field, e to the x sine y, I hat, minus e to the x cosine j hat at the point 0, 0, 3. What's that? Oh, cosine y. Those darn functions always have to put something in them. All right, so we're going to calculate the curl of this thing. So del cross f. And before we calculate the curl, I just wanted to mention in the last example where we found our conservative or our potential function. So we were doing integration with respect to integration of multivariable functions. So we've already thrown in chapter 14 into this first section of chapter 15. So we're already starting to mix all of our chapters together. So here's our curl: I hat, j hat, k hat. We're going to take our partial derivatives. This is where finding this determinant is where students often make mistakes with anytime we find a cross product. So be very careful when you find cross products. E to the x sine y minus e to the x cosine y and 0. So I'm going to do my determinant here. So I'm taking, crossing these out, the partial derivative of y with respect to 0, I get 0, minus the partial derivative of z of minus e to the x cosine y, so I get a 0 there, minus j. I'm going to take the partial derivative with respect to x of 0, so I get another 0. Partial derivative with respect to z of e to the x sine y, I get another 0. plus k hat. And for this last one, I get partial derivative with respect to x of minus e to the x cosine y. So I get a minus e to the x cosine y minus, and then a partial derivative with respect to y, e to the x sine y. So I get a minus e to the x cosine y again, and that simplifies to minus 2 e to the x cosine y k hat. And then at 0, 0, 3, so del cross f at our point 0, 0, 3, I get minus 2 k hat when I substitute 0 and 0. So the 3 didn't even come into play here. So that would be our curl of this vector field. And it's hard now to think about how this minus 2k hat would tell us about how that vector field is going to cause rotation, but we'll get to the place where, well, that will tell us something about our vector field. All right, questions on that example? So just a preview of where we're going. We're going to end up doing multiple integrals that have to do with the curl of a vector field over a surface. So we get to do a curl, multiple integral surfaces. They all get shoved together all in one problem. Kind of a nice thing. All right. So our test for conservative vector fields in space. We have a nice easy test. Our vector field of x, y, and z in space, and we're saying that's m I hat plus n j hat plus p k hat is conservative. If and only if del cross f equals 0. So if our curl is 0, if our field is irrotational, then our field is conservative, and it is the gradient of some potential function. This is equivalent to saying that the partial of p with respect to y equals a partial of n with respect to z. The partial of p with respect to x equals a partial of m with respect to z. And partial of n with respect to x equals a partial of m with respect to y. And all of these equations, all of these things being equal, follow from our mixed partials being equal. If m, n, and p are partial derivatives of some potential function, then these represent the mixed partials, and our mixed partials are all equal. So it's exactly like we talked about in the plane. These all represent the mixed partials of our function that represents our potential function. So these would be equal if this comes from a potential function. So we're talking about the equivalence of mixed partials. All right, so we have this idea of a vector field. We We have this idea of a potential function, the gradient of a potential function giving us a vector field, and how that relates to a conservative vector field. We'll talk later about what a conservative vector field conserves. We'll talk about what the potential represents, and we'll talk a little later about what the curl is telling us, a little more detail about what the curl is telling us about a vector field. So what I want to do, last thing I want to do is a test for a conservative vector field, and then finding, using, if our field is conservative, finding a potential function for a field in space. Is everybody good before we move on? Just talking about the curl and all this potential conservative vector fields is just, I just love chapter 15. When I was a student, it was, when we learned this stuff, it was, for some reason, it just really, I don't know, I just really liked it. And I was really like doing this chapter. All right, so this question is asking us, is F conservative? Is our question, and if so, find a potential function. And we have this vector field. F is y squared z cubed I hat plus 2x y z cubed j hat plus 3x y squared z squared k hat. So there's our long, kind of messy vector field. So first we want to see if F is conservative. So we're going to find the curl. So del cross F. And I'm going to make sure I have enough room here. I hat, j hat, k hat. I always like to write out my determinant this way, because if I don't, I make sign errors and it's harder to track them down. So here's our curl. And I'm going to form this determinant, so I'll go through this. This is I hat, and I'm going to take the partial derivative with respect to y of 3x y squared z squared. So I get 6xyz did I forget? Is that right? Did I write this? Yes. I just want to make sure I set up my problem correctly. Okay, so I have, take this partial derivative, I have 6x, take the partial derivative of this with respect to y, 6x y z squared, minus the partial derivative of this with respect to z, and I get 6x y z squared, minus j hat, and now I'm going to take the partial with respect to x of this. So I get 3y squared z squared. And then I'm going to take the partial with respect to partial with respect to z of this. So minus 3y squared z squared. Looks like it could be conservative. Plus, and for my last set of partial derivatives, I'm going to take the partial with respect to x of this, so I get 2yz cubed, minus, and I'm going to take the partial with respect to y of this, 2yz cubed, k hat, and I get 0, the 0 vector. So this field is conservative. Our curl is 0, so our field is conservative. To find my potential function, I'm going to integrate this component with respect to x, integrate this component with respect to y, and integrate this component with respect to z. So we know that f sub x, my potential function, f is conservative. I'm just going to write in a little notation. So f is the gradient of some scalar function. And this tells us that the partial derivative, this first component, tells us the partial derivative with respect to x of our scalar function is y squared z cubed. So I'm going to integrate that with respect to x. And I get x y squared z cubed. Plus, potentially, no pun intended, potentially we get some function of, I'm not going to use f because f is our potential function, h of y and z. Our constant of integration could be a function of y and z because it's a partial derivative with respect to x of a function of y and z is 0. And what we're going to do is do all of our integrals and make sure we don't have any stray functions of x, y, and z involved here that we need to keep track of. And just looking at these, we don't have this isn't y squared z cubed plus 1, so where I could potentially have a y or a z in there when I integrate. And this doesn't have a plus something. So I'm guessing that my functions, my constants of integration are just going to be some scalar constant. But we have to keep track because you could have a situation where you do end up with a function of one of the other variables that's your constant of integration. All right, so we know that our partial with respect to y of our scalar function is 2xy z cubed. So we'll integrate that with respect to y. And when we integrate that with respect to y, we get x y squared z cubed, plus we possibly could have some function of x and z. And then finally, our partial derivative of our potential function with respect to z is 3xy squared z squared. So we'll integrate that with respect to z. And we get x y squared z cubed plus some function possibly of x and y. Now because none of our components have any additional terms, we don't have a plus anything, we don't have anything else going on with each of these, the m, n, and p. I don't have a plus 1, I don't have anything else that I have to take into account. That tells me that my constants of integration are just scalar constants. So f equals xy squared z cubed plus, and I'll use c, plus some scalar constant. And my partial derivatives of this potential function give me my vector field. And those of you that did that bonus question on the chapter 13 test, you remember that was one function where we had to, our constants of integration turned out to be functions of one of the other variables. All right, questions on vector fields and the curl. Tomorrow we'll talk about divergence of vector fields, and then we will start talking about line integrals, I believe. Yep, so 15.2, we'll spend several days talking about line integrals. Line integrals are nice. It allows us to integrate the component of a vector field that's tangent to any particular curve. All right, homework. There we go.